and for the N1 patient, that's my pleasure to talk today here. And today, yes, as I mentioned, I'm going to discuss coherent systems and its derived category and its stability conditions, and this is based on the joint work with Sahila Fizik-Bash. And maybe before starting, going into deep math, I want to give a very general introduction of why should we care about this category and why can it be interesting? And I think the motivation is quite natural. So space of stability condition, this phenomenon of wall crossing has been proven to see a lot of geometry of the underlying variety itself, and so to kind of encode this geometric information. And so, for instance, in the Bruhl-Noether theory, we would like to apply some sort of the similar techniques, but the problem is that for the curves of genus higher than 0, it's been proven that the space of stability condition is trivial up to the group action. So in particular, it means that we cannot deform the stability conditions, and we cannot perform this wall crossing there. And so one of the ways of resolving this issue, one of the first known way, is just to take our curve C and put it on a higher dimensional variety, such as K3 surface, for which we know the stability manifold quite well. And what we can do is we can try to take the problem from the curve, try to put it on the ambient variety like a K3 surface, try to do the wall crossing there, and later try to see whether it gives us any geometric information about the underlying curve. And there are several, with this technique, several things and several results in Bruhl-Noether theory already were proved in that way, but it has its big drawback. First of all, we restrict ourselves to the curves which we can put on a K3 surface. And second of all, we can lose the information when we're pushing forward things from the curve to the surface. And today I kind of want to present an alternative approach to how one can construct a category in which we can actually have a non-trivial stability conditions, and maybe this category would be actually a good category to perform the wall crossing for the curve. And the idea is that instead of taking a curve and putting on something bigger, what we want to do is instead we want to enlarge the derived category itself. So instead of considering coherent shapes, we want to consider the coherent systems. And we want to study the derived category of them. And we also want to understand the stability conditions of this thing, and maybe for the further work to try to do the applications and perform the wall crossing there. And I think the main result, what we're going to discuss today, is that, first of all, that there exists we construct a two-dimensional slice of stability conditions on this derived category of coherent systems. And we also consider an open subset of the stability manifold, which we're able to describe completely. So this to be said, let me maybe go to more rigorous definition of everything that you can see in the title. And we're going to start with maybe defining the coherent systems themselves. So this is quite of a well-known construction that comes very naturally from Bruhl-Noether theory. So back in the day when people were trying to understand the maps from curve to different projective spaces, which is essentially encoded by a line bundle and sections. So, and we're trying to parameterize those line bundles, keeping the track of some global sections in it. They kind of came up with the idea how you can encode all these things in one go. So in particular, a generalized coherent system is just essentially a tripole of a vector space of a shape on a curve and some collection of global sections. So maybe before this, let me very quickly put it here, some notation that throughout the entire talk, see this would be an integral curve, smooth integral curve, over complex numbers of genus G, which almost always I would think about genus greater than 0. So we don't work with a P1 here. So, and coherent systems are those triples, such this is just a vector space, and F is just a coherent sheaf on our underlying curve C. And phi, this is just the collection of global sections that goes from this vector space to our sheaf F. And this is typically the way we denote the objects of our category of coherent systems. The only difference with it, why is it generalized and not just coherent systems? Because typically in the study of coherent systems, you want to look at the subspace of the global sections, and you want to consider only the kind of induced morphisms to the sheaf, or else we allow any sort of morphism just to be sure that this category is abelian. And so those are the objects of our category. They look like this, and the morphisms, I think, quite what we would expect them to be. So those are going to be just the commutative diagrams of the following shape. So if we have two different coherent systems, then the morphism on the bottom, this is just any morphism going in between the sheaves. But here on the top, we want to have just a morphism in between the vector spaces and tensor it with the identity morphism of a sheaf. So somehow, like on the very top, we do not allow any like sheafy morphism that can appear here. And we want this diagram to be commutative. And the resulting category with such objects and such morphism, this is going to be exactly the so we're going to denote it throughout the talk by TC, and this is an abelian category of coherent systems. And also by DTC, we will denote the bounded derived category of those coherent systems, where you just induce it from the abelian underlying abelian category. Okay, and also typically when all the derived categories here are going to be bounded, even if there is no B on top, I typically omit writing those things. Great, so this is the main kind of category we want to work with. And as I already mentioned, the coherent system, they have been intensively studied. For example, we know that it's been proven by Hare and 98, then if you enlarge your category to quasi-coherent shapes, then this category would have enough injectives, and therefore we can talk about injective resolutions, and therefore we can induce our, so we have the existence of our home on our derived category. And moreover, maybe a little bit important thing to notice is that this is the category of homological dimension 2. Homological dimension 2, it means that there are no higher x after 2. Great. So let's maybe, I know that some people already saw the coherent systems, but maybe let us have a look at them once again. So coherent system, this is just you take a shape essentially and attach to it a vector space and remember the morphism between them. So it's quite clear that, not quite clear, but I think it's quite natural that this category admits a semi-orthogonal decomposition where it decomposes in the derived category of a curve and the derived category of just vector spaces. So in particular, we can embed the derived category of vector spaces in our derived category of coherent systems in a very natural way. So just for a complex of vector spaces, you embed it into OC tethered with V to 0. And for the curve, for the sheaves on the curve, we just embed it also kind of the same very natural way. We just forget about it and just 0 to F. And the first thing to mention, maybe a lemma or observation, is that this indeed gives us a semi-orthogonal decomposition, as OC to 0 is going to be an exceptional object here, and the DC is going to be just the orthogonal to it. And why I wanted to mention this, because this semi-orthogonal decomposition essentially allows us to kind of use a bit of a form, to formally define what are the objects of the derived categories are and kind of have a handy way to work with them. Because so far, we define the derived categories just like, we start with an abelian category, later we consider the complexes, enlarge the homotopy category, and later we do the localization quasi-isomorphisms. But in that, if you think about it, it's just being glued from the derived category of vector spaces and derived category of the shapes. So in particular, it allows us to think about any object in this derived category is also triples, but this time we have that V belongs to this derived category, so this is just a complex of vector spaces. F also belongs to the derived category of coherent shapes on a curve, and this time phi is just going to be also a morphism as like a derived morphism in the derived category. And therefore, it's kind of like, this is a very handy way of thinking about the objects in this category in that case. Great. So this was kind of a definition that comes purely from the like more, not purely, but primarily from the Brillouin theory, like from this existence of coherent systems, but it also has a very nice geometric realization, and it comes from a bit of a different nature. So geometric realization, it can be constructed as following. So we start with our curve C, and nature, we can put our curve C on some Fano threefold. For example, it can be like, I don't know, P3 or any other Fano threefold. So this is Fano threefold. Because of the difference in the codimensions, what we can do, we can blow up our Fano threefold in that curve and get, so this is going to be a blow up, and we get the following picture. So this is blow up in curve in the center of the curve of our Fano threefold X. And then we know that by the blow up formula, we know that the derived category of a blow up has a semi-orthogonal decomposition, which essentially looks just like this. So this is the copy of the derived category of a threefold, and here we have a copy of the derived category of a curve. Okay, and since we've started with a Fano threefold, it essentially means that it also itself already has a semi-orthogonal decomposition, because then the structure sheaf of a whole threefold is exceptional object in that. So we can continue decomposing our derived category of a blow-up in order to obtain the following semi-orthogonal decomposition. And this piece here is essentially what? So this is going to be just isomorphic to the derived category of vector space. This is just one point on the level of derived category, and this is just the derived category of our initial curve. And it has been proven by Alexeyev and Kuznetsov that this piece here, it exactly is isomorphic to the derived category of coherent systems we're considering here. So essentially, it means that just the gluing in between those two things agrees in between themselves, because it's like, this is since the components, like since the semi-orthogonal decomposition already has the same components, everything we need to ensure is that gluing by module is the same on both sides. And it has been proven that this is exactly our derived category of coherent systems. This to be said, I want kind of to motivate the following idea that we're following here, is that we want to think that this category of coherent systems is kind of a natural non-commutative surface for the curve we are working with. Because it's like, the fact that it appears from two different perspectives very naturally, and also the fact that it, for instance, has a homological dimension too, and also it's it's quite easy to see that the Grothendieck numerical group is going to be just Z3, because what we have, once again, we have a sheaf, we attach a vector space, so sheaf numerically is controlled by two parameters, which is rank and degree, and we attach a vector space, which is controlled by the dimension of the vector space, right? So for every object here, we will have a class, which is just essentially, if we start with OCV to F to E, any coherent system, then the class of this thing in the numerical Grothendieck group is going to be just the rank of E, the degree of E, and the dimension of our vector space. So it has numerical Grothendieck group 3. We can also define the Euler pairing in order to give it a lattice structure. And also, I think, Alexeyev and Kuznetsov, they claim that in the upcoming work, they would be able also to show that the third dimension would be 2 of this category. The third function of this category exists just because it has a semi-orthogonal decomposition, both of pieces of which admit the third function. So it exists in the entire category. So this is kind of like a slogan that probably we want to follow, that this is a natural, canonical, non-commutative surface that we can associate with the curve. Great. So this is kind of what's the setup of the category we're working. And now I probably want to go to a bit of a different part, essentially to the stability conditions part. Because since we want to study the stability conditions of it in order to see whether we can do the wall crossing. So, so this is the stability conditions part. I know that probably many people already saw stability conditions, but I probably very quickly would recall the definition so everyone can refresh it in their mind. So the stability conditions can be defined in any triangulated category. And stability condition consists of the following pair. So it consists, first of all, of the heart of the bounded T structure, which we typically denote by A. So it's some heart of a bounded T structure on our triangulated category D. And Z is going to be a function that goes from the numerical Grothendieck group on our triangulated category D to the complex number and stability functions, function. Or similar, it's the same as just starting with the Grothendieck numerical group of our heart. So this is stability function wanted to satisfy several conditions. So the first thing is that we want that for any object from the heart, its central charge lies in the upper half plane merged with a negative real line. So in particular, we want that for every object, the central charge goes here or there, excluding the origin and excluding this positive real line here. So this is where the central charge wants to live in. Second of all, for every object, for any non-zero object here, we want it to admit Harder-Narasimha filtration with respect to the stability function. Harder-Narasimha filtration in exactly the same way it's did for vector bundles. So essentially, we just have a sequence of sheaves, and we want that the quotients of those, this is the quotient of those, would have the increasing phases here with respect to the stability functions. And so far, if those two conditions are satisfied, this is going to give us what's so-called the pre-stability condition. And in order it to be a stability, like a proper stability condition, we want also to have the support property to be satisfied. So what is the support property? It has a different definition, so maybe I will try to give both of them. So one of them is essentially saying that there exists a quadratic form Q. This is quadratic form on our lattice, so the numerical Grothendieck group D, such that if we have a stable object, semi-stable object with respect to this defined stability function, then we want that this form gives us something positive, and that also this form is negatively defined on the kernel of this stability function. Maybe for this, I want just to very quickly mention that since we defined the stability function only on our heart, but we peaked initially the heart, which is the heart of the bounded T structure, we can extend all this thing to the entire derived category, right? We can approach any object in our derived category with its kind of cohomology with respect to this heart, and therefore we can extend the stability function, the central charge, everything to the entire derived category. So this is one of the ways of thinking about the support property. An analogous way of thinking about the support property is just that the infimum of all those things where VE, this is just the class group in the numerical Grothendieck group, for each E being semi-stable with respect to the stability conditions of greater, so it's non-zero, so it's something positive. Why do we care about support property in general is because support property is something that ensures us to have actually a well-behaved wall crossing. So we don't have any situations when we have an infinite amount of walls or we cannot control the walls at all. So the support property is very crucial if we want to do a wall crossing and if we want to kind of apply those techniques there. So this was a very quick recap on what stability conditions are, and maybe I think it's worth mentioning that Bridgeland back in the day showed that with a suitable metric, all those stability conditions, they form a complex manifold. Which typically denoted by stab D, and also this complex manifold has a very natural right action of the universal coverage L plus 2R, which is essentially like, you want to think about it as like, so imagine yourself, you have your R2, and this is where your heart lies. Okay, and you want, essentially what this group action does, takes any orientation preserving linear transformation of R2. It acts like this on a central charge, and nature, everything else we allow also is just to shift it in a, so for instance, instead of considering just A, we can shift A to 1 or A minus 1. So this is the way we want to think about this action. And in particular, this action, it does preserve stable objects. But that said, if the stable object was stable before the action, then it's going to remain stable or semi-stable after this action. And so yes, and as an example, I think everyone probably already saw this example. We can just consider the coherent shifts on our underlying curve C, and we can consider the stability function being just minus degree plus I rank of our shift. And this is going to be a well-defined stability condition on our derived category of a curve. And to be said, this is going to be the only stability condition up to this GL2 action. So this is going to be the only interesting stability condition. So this is exactly what Macri proved in 7, that the stability manifold of every curve of genus greater than 0, here it's very important that we consider only the curves of genus greater than 0, is essentially equivalent to this. So this action is free and transitive. So so yes, up to this action, the stability manifold is essentially one point given by this mu stability. And kind of why is it happening in that case is, I think it's a very particular case to the curve, because first of all, it's very important, and the derived category has a homological dimension 1. So essentially, we have a very good control over all the elements of the derived category with this cohomology, because it's going to be just isomorphic to the direct sum of the cohomologies. And this allows us to control all the possible Hardener destabilizing sequences for structure sheaf of points and also for line bundles. In particular, what one can show is that every structure sheaf of a point and every line bundle are going to be stable for any stability condition and in potential stability condition derived category of the curves, precisely because we have a very good control over the destabilizing sequences. Great. So this is what I wanted to say about the general story of the stability conditions and nature. I think it's a very good time to start kind of merging those two things, and to construct the stability conditions on these derived categories of coherent shifts, or coherent systems. Construct stability conditions on this derived category of coherent systems. So once again, what our was, and in particular, we want to study the following open subset of this, want to study the following open subset of the stability manifold, such that in this open subset, we want to impose that this object and also this object, for any point, they are stable for those stability conditions. We want to study this open subset and want to be able to control the entire open subset. And yes, as I said, so once again, so our coherent systems, this is just we take a shape and we attach a vector space. And recall we had this very nice orthogonal decomposition, and it's a very general also fact that as soon as you have a semi-orthogonal decomposition, you have these gluing techniques of the stability conditions from both of the components if they admit those components. So in particular, one first type of stability conditions, which we call time A, they just arise from gluing constructions, gluing stability conditions. This is the general theory that is developed by Collins and Polishchuk back in the day of how you can do this thing. And it essentially, it's kind of very, it's quite clear what do we want to do. So here we have, for instance, this is just essentially the derived category of vector spaces, right? We can put there just a trivial stability conditions where the central charge looks like this, and the heart, just essentially all the complexes concentrated in 0 degree. And on the DC, we have those stability conditions that we kind of parameterize by the elements of the GL plus 2R action. Okay, so this is all those stability conditions. And under a suitable choice of this element G, we can glue the stability conditions. We can glue them in such a way that glue it hard heart is going to look like this. So in order to glue the heart, what we do, we take an object and we just consider a natural exact triangle that comes from the semi-orthogonal decomposition. So we take an object in our derived category and we consider, was it a question? Was it no? Okay. And so we consider something like, so we consider the natural triangle. And what we want from this thing, in order our object T, this is my object T, we say that the object T lies in the heart if just both pieces do lie in the corresponding hearts. So if this lies in this A0 and if this lies in this AG. Okay, so we just consider all the possible extensions in between those two hearts. And also the stability function is then going to be just the sum of the previous stability functions plus this stability function we have on the vector spaces. So in general, those stability conditions, yes, they are kind of interesting, but they do not provide any new, some sort of like, they still very highly dependent on the stability conditions we used to have before, right? And in particular, like, for instance, if I just start, like, I don't know, if I start with a mu stability condition on a curve, and if I shift it far enough, then it would essentially mean that there are no non-trivial extensions, right? Because if I shift it far enough, so it like every non-trivial extension is going to vanish. So there are interesting stability conditions in this like case, but they do completely overlap with the second family I'm going to introduce right now. And the only ones that do not overlap, they do kind of have almost trivial heart, which is not that interesting to consider for the case of wall crossing. And the second type of stability conditions I want to introduce is kind of, it comes from this idea that we want to think about this category as being like a canonical surface. So, and this is essentially this tilting construction or tilting stability conditions. Maybe in comparison with what have been done for the K3 surfaces case. I redrawn in 08. So how does typically tilting stability condition work? So we start with our derived category admits a very natural abelian underlying category, right? So this is just coherent systems. So we start with this category of TC, and later we introduce the stability function in it. And the stability function that is typically studied in coherent system, this is mu alpha stability. Which essentially, for every object like this, it just would be equal to the degree of E over rank of E, plus this alpha parameter over the dimension of V over the alpha greater than 0, over this rank of E if rank is non-zero, and plus infinity if the rank is 0. Okay, so this is a very natural stability function defined on these coherent systems. And in particular, for I think for the rest of the talk, we would be primarily interested in the case when alpha is just equal 0. So we kind of forget about the existence of the vector space, and we just capture the slope function only on the underlying shift. And we construct the tilting stability conditions only with this kind of mu stability condition, which is essentially, as I said, this is just the case when alpha is equal to 0. So it's just the degree of E over the rank of E plus infinity otherwise. But we'll also see that in our stability manifold, we'll be able to recognize mu alpha stability when we go to the large volume limit. So in that case, we start with the TC and we have this stability function. And if, for example, we just kind of naively try to consider the same thing as for curves when we had a stability function and we defined a stability function from the perspective of the stability condition, then it's going to be minus degree E plus I rank E. You can see that it does not define a stability function from this perspective, just because, for instance, if you take an object OC to 0, then we'll get that our central charge from it is going to be just equal to 0, right? So it's not where it needs to land. And therefore, we try to tilt the initial heart with respect to this mu stability introduced right now. What does it mean that we tilt the heart? It's some sort of, so we have this is our heart. So on the very top, we have this our category of TC. And what we do, we just pick some slope and we split our category of the coherent systems on the two halves. And we put one of them as being the torsion part of it, and the second part as being the torsion-free part of it. And later, we kind of, instead of considering the category that consists of the torsion and torsion-free part, we just move the torsion-free part on the other side of this torus. So we kind of flip it here, and we consider FB1 instead of the previous one. Let me maybe make it a little bit more rigorous. So TB is going to be all those coherent systems such that mu minus is going to be greater than B. Mu minus, this is the smallest piece of the hardened Arcima filtration. And if B, those are going to be vice versa, all those coherent systems such that mu plus is bounded by B. So it's kind of, you want to think of TB being just a subcategory closed under the extensions of all stable object with a slope less than B, and FB is vice versa. And we then consider the hard, and we then consider the category, which is essentially generated by this torsion pair. And this is well known to be a bounded derived category, or bounded heart of a bounded derived, heart of a bounded T structure. So this is a very natural candidate to have a stability function, a stability condition with. And in order to define the stability condition, we also need to define the central charge, right? And in order to define the central charge, we'll need to define firstly the Brill-Noether function on this category. So the first thing to do is to define the Brill-Noether function on this category. And so we define the Brill-Noether function on this curve in the following way. So this is going to be the ellipse of going to x of just this quantity when we divide the amount of global sections over the rank of f, such that f is a sheaf, this time on our curve C, which is semi-stable, which is mu semi-stable, and such that mu f is just equal to mu. So this is a very similar to this Le-Portier function thing. And so maybe let me quickly kind of give a general idea of how this function looks like. Is that first of all, when we have x less than 0, then we obviously will get something less than 0, just because there are no global sections for semi-stable sheaves of negative slope. Also after the moment of 2g minus 2, we can do the Riemann log, and therefore this here will essentially also get just a line, which is if I'm not mistaken, this equation. By Riemann log, and here we will have some sort of upper semi-continuous function, but we don't really know very precisely how this function behaves. But this is going to be this function is well defined, and this function is clearly upper semi-continuous. But it can have a very kind of not an ugly shape, but very unclear shape. It can have also jumps, for instance, on this part. So this is how what is our Brill-Noether function is. And now we have all the components in order to define, in order to state how can we define those tilted stability condition. Let me start, that is maybe, I don't know, theorem 1. So what we show is that there exists a two-dimensional slice of stability conditions that are parameterized by B and W that belong to R squared, such that we want our W to be greater than the value of this Brill-Noether function at the point B. Of stability conditions, we denote them with two parameters, B and W, such that the hard is just AB and the central charge looks like this. So this central charge is for some object T, it's going to be T plus I d T PRT. So I think this is kind of very similar technique as had been done for the K3 surface and for the surfaces in general, how you can define them. And maybe let me say two words of how one can of what is happening in the proof. So the first thing is that we want to show that this is a press-stability condition, right? And in order to actually say that the central charge is well defined, in particular that it lies in this upper half plane and the negative real line, it kind of this Brill-Noether, the fact that we've bounded our choice of W with a Brill-Noether function, it ensures that in fact that it would satisfy, like it would belong to this upper half plane plus the negative real line. So Z is a stability function. It's kind of really ensured by the Brill-Noether function, by this choice. And Hartner-Arcima filtration is typically also for tilted stability conditions. For tilted heart is a very kind of like, you show it kind of like based on the fact that every element in your tilted derived in a tilted heart just has minus first cohomology being in the torsion-free part, and the zero cohomology being in -1 in torsion-free part and 0 in torsion part. And maybe the interesting thing to prove here is how to go from the pre-stability condition to the classical stability condition. In particular, how to ensure that we have a support property satisfied for those stability conditions. And here we use kind of like a trick that we want to understand firstly. We firstly understand the large volume limit, because so once again, so we can draw our stability conditions on kind of like on a plane where this is just our Brill-Noether function, right? And every point corresponds to some stability condition. And firstly, what we do is like we analyze the large volume limit here. So what would happen if, like, for instance, we have an object T, which is semi-stable for every stability condition if we put W to go to infinity. In fact, the large volume limit here would recover completely the mu stability here. So if we have that something is semi-stable in large volume limit, then it's just going to have either 0 cohomology or minus first cohomology being just mu semi-stable. And therefore, for those objects, it's very difficult. Like, it's very easy to show the existence, for example, to show that the quadratic form we're considering would be indeed well defined. And for the rest, what we want to do is that we want to do some sort of an induction. Want to do an induction on the image of ZT. So kind of like we can construct we can give kind of a candidate for the support property on the for the quadratic form of the support property. So we consider the candidate of the support of this thing. So it's going to be something like this: T minus B0 plus minus n r, where this delta is peaked in a very particular way, and nature would just do the induction. So if we start with the base when it's 0 or minimal, then we essentially can ensure if it's 0, then it's very easy to see that it's indeed the quadratic form is positive on the, is not negative on the stable factors. And if it's minimal, then we know that since the destabilizing factors needs to have imaginary part less than this, we know that if we push it to the large volume limit, that it needs to be semi-stable in that case. And nature, what we do, we kind of just really do the induction on the imaginary part. So each time we kind of go to the next step, we want to use, and we consider like an object T which is semi-stable with a bit higher imaginary part of the central charge, which we know that if it destabilizes at some moment, then we know that its both components would have the imaginary part strictly less, right? So, and we also know that, and if it's not semi-stable on the, if it's semi-stable in the large volume limit, that the inequality is definitely satisfied. But if not semi-stable, there is a moment in which it destabilizes, and the fact that we have the support property for the lower, for its kind of pieces of its Hartner-Arcima filtration, means that it already for this very particular object already the wall crossing is well behaved, so we can consider this moment when it's strictly semi-stable, and this would essentially ensures us that in this very particular moment, we can show that the quadratic form is greater than 0. I think it's a very general trick of how to do the induction on the, not a very general trick, but it's just a trick of how one can do the induction on the imaginary part to show that the support properties is satisfied. All right. So probably next thing I want to talk about is that essentially that the following. So one of our kind of main results, so we show the existence of this two-dimensional family. We also have this glued stability conditions, right? And now what we can show is that those two types of the stability conditions, they in fact control the entire open subset we're interested in. So let me call it maybe theorem 2, is that up to GL plus 2R action, any stability condition in this open set we're considering, let me maybe also very quickly recall that this open subset is where all the stability conditions such that OC and 0 to Kx are stable. Then the sigma is necessarily needs to be of one of the following types. So it's either type A, so it's glued stability condition from this semi-orthogonal decomposition OC to 0 and DC, where here we impose the trivial one, and here we want, if we consider sigma G, then we want f of 0, and if this G as an element of GL plus 2R has a form of M and F, where M is this linear orientation preserving map on R squared, and F is the increasing function, then if this is less than 1/2. And the second type is that we have exactly those tilting stability conditions. Which were previously denoted by those two parameters, which such that. So essentially, this result says that for every sigma, for every sigma, we have that it's one of those two types. And before we kind of show that those both types, they do exist. So it means that it's like a necessary and sufficient result that completely describes this open subset here. And moreover, yes, as I mentioned before, those two families do overlap. And it kind of helps us to describe that. I mean, we also can describe just the stability manifold. It's kind of like, imagine yourself, we have a two-dimensional parameter family in our stability manifold, and later here on the one of the side of it, we do attach those gluing stability conditions, right? And maybe I want to say a few words on how one can show this, but essentially by imposing the stability of those two objects, OC to 0 and 0 to Kx, what do we have is that we kind of get an access to control precisely what is happening in the heart. So typically what we do is like we fix the face of 1. So we put this to the face equal to 1. This is like, we can always do this by this GL2 plus by the action, right? We put it in the face to 1, and later we want to see whether the face of 0 to Kx lands. If it lands in the heart, then it would result into the tilting stability condition. But if it goes outside this, then it would result to the gluing stability conditions. But the fact that we have both of those objects being fixed and being stable allows us to compute essentially, like, the cohomology of the objects in the heart and understand their geometry, right? But in general, it's very difficult to do this with like if we drop, for example, the stability of one of them. For instance, what we else can show is that if instead of, because I think the general dream would be to understand this kind of all the geometric subspace of stability conditions. So when we only fix the stability of 0 to Kx. But unfortunately, just fixing 0 to Kx does not allow us yet to control the entire heart or to control the entire manifold so far. But what we can show that is that, for instance, if we replace it with a 0 to OC, and now we impose 0 to OC or 0 to Kx being stable, then we can also control all the stability conditions. And they would come into two different families, and they would but both of those families are going to be gluing stability conditions. So then if those are stable, then this open locus would be described as gluing from our fast SOD, OC to 0, and to C. This is in the case when it happens that OC to 0 is stable. And the second one, when OC to 0 is not stable, after they imposing the stability of this extra object, we have a full control of the Harder-Narasimha filtration of this of OC to 0. And therefore, since we have a full control of it's going to essentially come from this second semi-orthogonal decomposition, when now we consider this to be a second exceptional object. So far, all stability conditions we understood is kind of like this nice two-dimensional family, plus on one side we attach one type of gluing, on the second side we attach the second type of gluing that comes from another semi-orthogonal decomposition, right? And maybe what I want kind of to say more to in the end, I want to talk a bit about the walls and chamber decomposition, and in particular how one can recognize the alpha stability from the large volume limit. And so let me say several words about walls and chamber structure. So I think in general, we want to consider this walls and chamber structure on this two-dimensional slice we have. And I think in general, it's very convenient if you kind of draw, so we have that let me maybe draw it like this. So this is, once again, this is our Brull-Noether function, and here our stability conditions, right? So each point corresponds to a stability condition. And what else can we do? We can introduce the homogeneous coordinates for, so if we have an object T of some class, I don't know, RDN, then we can, for this object T here, we can introduce the homogeneous coordinates, right? And what we can do, we kind of can draw those two things on the one coordinate plane. So instead of it just being B and W on the very pair, we want also it to be those second pair of coordinates. And now we can also draw the objects here. For instance, this is going to be my class V. And then wall and chamber structure in this very particular case becomes very kind of simple, because all the if we start with an object such that rank is non-zero, then the walls would be just essentially straight lines passing through this point V here. So those are the walls. Okay, maybe here it's better that they're going to be terminating on the boundary of this manifold, but this is how those walls would look like. So they will be terminating on the manifold, but this is going to be those are going to be just like the straight lines. But the only small issue here is that, as I said, the Brull-Noether function, it's not convex, right? And in general, I think what we expect is that if we have, so in particular, if we have something like this here, then if we have our vector here, then we can potentially have a wall just looking like this. And later it terminates after the first spot, and like it's a bit unclear how they would interact, for instance, with the second chamber. So we can have potentially some situations like this. And also, we cannot say so far that, like, if you consider a semi-stable object, it would always lie under the Brull-Noether function. The best we can do is just to take the convex subset here. So instead of considering the entire half of the plane that lies above the Brull-Noether function, we consider only the convex part, and then we can say that the projection of the semi-stable objects in this thing is going to lie outside this convex thing. But we still do have kind of this part here, which remains a bit unclear. I mean, Clifford Clifford theorem gives us kind of like a good approximation for this region, but it's still there is still a space remaining below and in between the Brull-Noether function, right? And so this is how the walls and chamber decomposition is going to look like. And in particular, if we consider, so yeah, I'm going to do this once again. So if we consider here some class also V, so before we're able to analyze the vertical walls, I mentioned it, right? So this is if the vertical large volume limit. So if we have a vertical large volume limit, on the top would go just to mu stability. So this is mu alpha stability when we fix the parameter alpha being 0. And now if we consider right now the line that goes like this, of the slope minus 1 over alpha, and one of the things also will show that if we consider here some stability condition that already is on this negative part, like whether B0, if B0 is less, okay, maybe proposition. If we have B0 and if our some object in our derived category of coherent shapes is semi-stable, such that its class equal to our vector v, it's semi-stable. In this stability condition B0 W0, then we know that it's going to be semi-stable on the very rest there, so it's kind of going to be semi-stable. It's in this large volume limit going on the line that goes not on the straight on this line and in the infinity. Then essentially it's going to happen if and only if T is mu alpha semi-stable up to shift. So it can be a shift, but it needs to be then, we need to start with a mu alpha semi-stable object. So this is what I kind of meant, that we can still detect this mu alpha semi-stability in our stability manifold, right? And maybe to kind of in last 5 minutes, what I wanted to say is probably what we can do further, and because so far this is kind of like what I've presented today. This is kind of just setting up the environment in which you want to work at, and as a natural continuation of this work, it can be, first of all, of course, it's to do some applications. Maybe I think the primary application that right now we're working at is applications of the wall crossing to the Butler's conjecture, and this is the first thing to do. And the second thing is to understand further the stability manifold. Maybe understand, I don't know, the entire open subset of geometric stability conditions. Or also an interesting question to think of is that Alexeyev and Kuznetsov showed that there are very Alexeyev and Kuznetsov showed the existence of kind of exotic exceptional objects in this category. Namely, those exotic exceptional objects that are coming purely from the geometry of the curve. So if you have your curve C, then you can consider a line bundle. L is a line bundle, which is called Brill-Noether-Petri line bundle. If we have the following map being an isomorphism, following a natural map being an isomorphism. See, and this goes to C omega C. So, and we call it Brill-Noether-Petri if this map is an isomorphism here. And it has been shown that those line bundles do exist if we consider a general cup C over an algebraically closed field of characteristic 0, and they do exist for any sort of decomposition of a genus of the curve, because that would essentially impose straightforward that H0 of E times H1 of E is going to be equal to G, right? Of L, sorry, of L, here's L. And for any such decomposition of your genus, you will have this line bundle that would satisfy this isomorphism. And later, if you consider an object in your derived category of coherent system, which is essentially just taking all the global sections and going to your line bundle, then they proved that this object is exceptional. And therefore, you can consider a semi-orthogonal decomposition with this. thing. And also, moreover, what they proved is that this complement is not going to be isomorphic to a derived category of the cup. So you get some sort of a derived category which has a Grothendieck group, numerical Grothendieck group of rank 2, which is not isomorphic to the derived category of the cup, which essentially provides an example, counterexample for the Jordan-Holder conjecture. But it would be, for instance, very interesting to study also whether this category admits stability conditions or not. And maybe the fact that it admits maybe would induce, I don't know, some sort of new stability conditions on the entire category, because, yeah. Or it would be a nice example of something like of a derived category that has the same numerical properties of a derived category of a car, but maybe one can show that it does not have any stability conditions. I don't have a very precise answer to this yet so far. So yeah, I think that on this moment I want probably to stop. And do you have any questions?
Thank you, Sasha. Can we all please unmute ourselves and give the speaker a round of applause? Yeah.
Thank you.
Right, so if you have any questions, please ask them.
Yeah, I have a question. What do you have about the Butler's conjecture? Do you have, for Butler's conjecture, you say that you have some application?
I think that they're trying to prove the Butler's conjecture with this wall crossing technique on the stability manifold.
Or have you succeed? Somebody succeed to prove it, or?
I think this is something maybe you can ask directly Sahela about, because I don't really know the stage of the project so far.
Okay.
Yes.
Very nice talk. Thanks.
Thank you.
Thank you. Any other comments or questions?
Sasha, I had a question. So you have that this derived category of coherent systems is homological dimension 2, so it looks like a homological surface.
Yes.
Do you know whether it deforms to like an honest-to-goodness surface? Like you have this geometric realization in terms of this blow up the Fano variety along the curve. So maybe it's deformation equivalent to some surface inside that blown up Fano threefold, for example.
This is a very good question, but I'm not sure that this is true, because you can compute. I think that under the deformation, the Hochschild cohomology are preserved, right? And Hochschild cohomology for these things are computed, and I don't think that it would agree with any other surface.
Oh, interesting. So it's an actually honest to goodness, like new
I think
surface.
I would I will need to double check it, but I'm quite sure that it's not deformational equivalent to a surface.
Okay, that's pretty cool.
But I'm gonna double check it.
No, I appreciate that. Okay, thanks, Sasha.
Thank you, Nick. Any other questions? Anybody? So at the end, when you said that this theory or this work can be used to understand the whole open subset of geometric stability conditions, is that something that's been done already, or is that like a possibility?
Can you please repeat the question?
So at the end, when you were discussing applications, under number 2, you said that one might be able to understand the whole open subset of geometric stability conditions. So has that been done already?
I was trying to discuss the future directions.
I see. Okay.
So yeah, that would be nice if we can understand. Or it would be nice if we can see that we cannot understand. So this is just one of the possible directions one can go to.
Okay. Thank you. Any other questions? We don't have any more questions. Let's thank our speaker once again.
Yeah, maybe very quick. I'm sorry.
Yeah, go on.
Very quick comment. As far as I do remember, if you compute the second Hochschild cohomology, then it's going to just essentially have the deformations coming only from the cap. So I don't think that it would agree with any surface.
Well, this is in relation to next question.
Hmm?
Okay. This is in relation to next
No,
question.
that was to Nick.
Yeah.
Yeah, sorry.
Oh, so you only get deformations from the curve.
Yes, I
Okay,
think
that's interesting. Yeah, it's a fun idea. I really like the idea of finding this homological surface rather than embedding into an honest-to-goodness surface.
Yeah.